This is the cheapest lens in the world because its cost is equal to the cost of this cheap polyethylene film that is used in greenhouses. When rainwater fills the film, it turns into a curved surface that focuses solar radiation into a similar spot, which creates a high temperature of several hundred degrees Celsius. We now see evidence of the high temperature created by a water lens, and we see that it is capable of igniting paper or heating a frying pan for cooking. If we want to generate electricity, we can replace this frying pan with a Stirling engine that powers an electric generator, or this spot could be the site of a small solar panel that would receive several dozen times more solar radiation than a conventional solar panel of the same size. The third option is to replace this frying pan with a similar receiver that converts solar radiation into heating of a heat transfer fluid with a temperature of 200 or 300 degrees Celsius in order to generate electricity by a turbine, and I will describe this option in more detail in 2 minutes. We know that 1 square meter of this transparent film costs about 20 cents, and its lifespan will be about 1 year, during which the sun will direct this amount of solar energy onto the film, but only 20% will be converted into the thermal energy. Now we can quickly calculate that the cost of the thermal energy is like this, and it is approximately 100 times cheaper than the cost of heat from natural gas, and therefore we can be very happy that we have made a great invention, which is a huge breakthrough in the world energy sector. Unfortunately, the real cost of this solar heat will be many times worse than what we calculated with this formula, and therefore I will now describe 5 problems that increase the cost of our solar energy from these lenses. I remind you that my videos promote a different way of generating solar energy based on very cheap mirrors. That is why my previous videos described my experiments with 8 types of cheap mirrors made from glass rectangles, from sheets of stainless steel or anodized aluminum, and from this cheap reflective film on porous plastics, concrete, steel sheets, and steel structures. If you come to the conclusion that I have exaggerated those 5 problems of the water lenses or invent a way to solve them, it means that this idea has a chance to make a breakthrough in the world energy sector, and therefore perhaps one day we will see solar power plants of this type with millions of such cells, each of which is this square of transparent film with this puddle and other devices. I was planning to do a lot of experiments on this topic, but I am in the army now, and maybe someday, after the war, I will make a more experimental video. Unfortunately, water mass transmits significantly less solar radiation than the glass of a conventional lens, and therefore this value requires reduction. The first reason is that water absorbs almost all infrared photons, while infrared radiation carries approximately half of the energy that comes from the sun. It is obvious that the second reason is dirty water and dirt on the surface of the puddle and at its bottom. We understand that each cell must have this film and this water, and here we must install a receiver, which is the focal point of the solar radiation that is absorbed by this dark surface. As a result, the dark surface heats up to a temperature of several hundred degrees, and this heat is transferred to a heat transfer fluid with a temperature of 200 or 300 degrees Celsius, which circulates here. The hot fluid transfers the heat to a turbine to generate electricity and heats large masses of concrete, sand, soil, or other cheap materials. The hot masses provide the energy to the same turbine at night, and this is a big advantage over solar panels, which produce a lot of electricity only during the sun. All these processes are similar to the processes in solar power plants of this type, where these mirrors focus solar radiation on this receiver that is a path for circulating thermal oil, which is heated by the solar radiation to almost 400 degrees Celsius. The hot oil transfers the thermal energy to the turbines and heats the molten salt inside the tanks so that they provide heat to the same turbines at night. It is desirable that the diameter of a water lens be approximately equal to this distance between the lens and the receiver, but now I am showing you experiments by different people, and you see that the distance is 3 or 5 times larger than the diameter of the lens. Unfortunately, we cannot reduce the distance radically due to lens aberrations and other reasons, and this fact leads to an increase in the cost of the receivers and a decrease in their efficiency. In addition, this fact leads to a decrease in the heating temperature of receivers, although these experiments with paper ignition tell us that the heating temperature can be 200 or 300 degrees Celsius, but I doubt that it can be higher. We know that the sun moves from morning to evening, and therefore the receiver must also move. Unfortunately, the aberrations of the water lens will cause the generation of thermal energy to take place only now, during these 4 or 6 hours around midday, but now in the evening those aberrations will cause defocusing. A similar defocusing will take place now in the morning hours. That is why this value will be smaller, because we must subtract the solar radiation of the morning and evening hours. It is obvious that the receivers of adjacent cells are connected to each other by this pipe, similar to this my experiment, where these 3 receivers have one device for their movement. This pipe is the circulation path of the heat transfer fluid, but our receivers will unite into large meshes of several hundred receivers. You see that the area of this water lens is several times smaller than 1 square meter of the area of this film, and therefore we must reduce this value several times. Another problem is that this system works well near the equator, because if this angle of incidence is more than 30 or 50 degrees, the aberrations of a water lens destroy the focusing, and therefore the efficiency of the thermal energy production is radically reduced. If we are located far from the equator, we must use a different type of water lens that does not require an exclusively horizontal position, and this option will be analyzed in one of my future videos. Of course, you may notice other problems with these systems, and for example, we must maintain a certain water level, protect the water from pollution and algae, take into account the stretching of the film over time, and withstand hurricanes, hail, and other weather conditions. I have compiled several formulas to understand the energy and economic prospects of that solar technology, and this is the first of the important formulas that predicts the heating power of the thermal oil by the solar energy from 1 square meter of film at noon near the equator. You have the opportunity to object to my estimates of these values, and you can also understand what influences this thermal power, which is used in the following formula to estimate how much thermal energy is produced from 1 square meter of film during 1 year. This estimate is used in the following formula, which leads us to this cost of our solar thermal energy in the equatorial regions, and we take into account not only this cost of the film and its lifespan, but also the cost of the remaining parts of the system, the cost of land, and other factors. On the one hand, this cost of our solar heat is good, about 4 times cheaper than the cost of heat from natural gas. That is why it is economically viable to use this solar heat in industrial processes of factories or for other purposes, and thermal energy at this cost can be used to generate solar electricity at a cost of 8 or 10 cents per kilowatt hour. But on the other hand, this heat is 2 or 3 times more expensive than the solar heat from my cheap mirrors, although you have the right to disagree with me and prove that these cheap lenses are better.